All right, so let's get started. All right, so I'm a little bit under the weather, so I will try my best. So we're going to move into module 3. That's about like 3D. So the first lecture will be about like perspective geometry and camera models. Okay. So, but before that, let me try to kind of or provide a kind of quick overview of what we have talked about so far. So this is the most important things that for your homework 3, that is about correspondence, right? Once you like have feature matching, if you have correspondence, and then how do you actually solve for the missing solve the transformation between these two point sets? So we talked about this earlier, where you basically what you do is that you transform the correspondence, the mapping between x1, y1, and the x1, y1, and then expand that and then reshape this. The missing part is the column vector, and then prepare this known matrix of A and B. Okay, and you can solve it. Yes.
I'm sorry, what's T1 and T2?
T1, T2 is the translations. So here is this part is scaling and rotation, and this one is translation. But the work that you'll be implementing is the homography. That's most general, right? So you have the whole 3x3 matrix. Okay. All right. So and basically you have in this affine transformation, there's a simple transformation. You have 6 unknowns. So what you do is that you basically solve for this, put the unknowns into a column vector, and now you have a linear system of equations. If you have 3 points, then you can because every point pairs give you 2 equations. So which means that you need 3 correspondence pairs to solve for this. Okay, so it looks like this. You have 3 points, and then you get you can figure out what the transformation between them. All right. And in homework 3, you are doing this for 4 points. Okay, for 4 points for the correspondence. All right. So where are we having talking about in this in the whole class? So we start with the color, then we talk about filtering, multiple different filtering perspectives from spatial domain to frequency domains, and to how you apply filters to form pyramids for the Gaussian pyramids, and to do downsampling. Okay. Then we talk about the correspondence, right? So in the last part, we talk about feature correspondence. How do you extract edges? How do you extract corners? How do you extract interest points? And so one important part is called speed features. That's when you have 2 images, you can detect the speed features, and you can match them, right? And that's the application you will be implementing. So we already implement that speed feature matching part for you, but you can see how everything put together. Like once you get the correspondence, you can, and then you solve for the transformation, you can stitch images together. And that's actually very exciting. I think around 2000, 25 years ago, that's probably the first computer vision algorithm that's made it to commercial space. Like that's when every cell phone would have this homography that has this image stitching. Okay, nowadays it's kind of pretty common these days. You probably cannot find a phone without this homography. But this is actually when things actually start working in the computer vision space. Okay. And we also talk about that once you have these features, kind of detect what are the salient points, you can also track them over time, right? So we talk about this. This is where the homework 2 is about, and we specifically talk about Lucas Canade that you can track, so you can do motion analysis. Yeah, and for fitting alignment, we talk about multiple different algorithms. So specifically, this square approach, where you have an objective function, you solve for this, or the half transform or the RenSec. Okay, so you mostly use RenSec more. Yeah, but you should also be aware of others. All right, so what we're going to talk about in this in the third module is first one is this lecture. We'll talk about like basically we want to understand what is the mathematical model between a 3D point in space, and if you capture an image, and what is the and if it's a point, and if I capture that point in the 2D image, it's just x and y, right? Just two-dimensional point. What is the relationship between that 3D XYZ and the X and Y in the image space? So we want to build the relationship between these two. And the reason why we want to build this relationship is that later on, if you have multiple images, look at the same 3D point, you will be able to triangulate that 3D point. You're going to solve for 3D reconstructions, okay? So this is where the 3D vision comes in, where you not only describe everything that's in the image plan, but also you can understand what's in 3D, okay? So this is the first lecture. We'll basically mostly talk about the camera model, and we'll talk a little bit about lenses, and then we'll talk about single view metrology, basically from what can you tell from a single view images. How do you kind of measure sizes and so on. And then we'll go into details in the photo stitching. In the homework 3, you'll be talking about stitching, but most of the part is already implemented. You only handle the homography estimation part. But there are a lot of details that feed into image stitching. That's basically the image stitching revolves two cameras. There are two views that are rotating camera, right? So one camera capture a photo and you rotate, the camera center does not change, take another photo. And that's a relationship between image stitching. And for two view, but for a camera that's translating, that becomes the stereo problem, stereo vision problem, okay? So there we will talk about some basic geometry inside this stereo visions. And if you have multiple views, and it becomes the structure for motion problem. So basically the problem is I give you multiple photos, and then how do I estimate where the camera is and what is three-dimensional structure of the scene, okay? So this has a lot of application in robotics, in kind of architecture, like preservations of monitoring, structure, building, and so on. Okay. So this is what we're going to do in module 3. So let's start with the very simple thing. Okay, so I have a sensor, I have a scene. Let's say this is it's just a tree. How do I if I have a sensor in front of the tree, would I get a clean image if I do the exposure? Any idea? What would this image look like? If I have a sensor, right? So it's like any sensor on my phone, I put a sensor in front of a tree. What will happen in this case? Would I get a reasonable image? Do you think yes? Any idea? What could go wrong in this case? No. I mean, I can make it properly exposed, but I'm just saying that what will happen if this? How will the sensor record this scene well? An image of this tree. Yes.
I can't tell if you're talking about in like a 2D plane, but if that's what you're referring to, then it would just see like the side closest sensor. I've got a real tree and a real sensor.
Yeah, so and of course this looks like a cartoon, but let's imagine this is a 3D tree. But I have a sensor, and you can just imagine that we are looking at that from this angle. It's still a 2D sensor. I'm just saying that like what would happen if I try to capture this tree? Okay, so let me give you some hint, right? So if I have this what will happen is this, right? So the light coming from the top of the tree, they will, like, of course, the light will hit those tree and they will reflect this light, right? Part of the light, that point will come into the sensor, right? And the bottom of the tree also will come into the sensor. So what will happen in this case? Would I get a clean image? So you can see that now every pixel records this pixel, every pixel records both the light coming from the top of the tree, also the bottom of the tree. So what would that image look like? Yes.
It would just be a combination of the pixels.
Yeah. Sure. It will be kind of like some mixture, right?
Huge Gaussian.
Yeah, it will be very, very blur, right? So this is obviously, but our camera doesn't do that, right? So we can capture clean, sharp image. So one of the key idea here is that one simple model to solve this is that because all these lights are kind of pencil, like they move at the same location, right? So key idea for solving this, people solved this in like 2000 years ago, is to use a barrier. Okay, so I introduce a barrier in front of my sensor, so that now all the lights come through this. Most of them will be blocked by the barrier, and only very few of them will pass through the barrier. Okay, and now because of that, every line, every point in the 3D scenes will project onto the very clear point. Like every pixel records only one part of the very small part of the scene, and this is why you get a clean image. Okay, so we typically call this center projections. So we'll revisit the design later on, but let's try to understand the geometry of this problem. Okay, so of course it's a 2D thing, look at the 2D thing, but let me try to kind of, you can imagine this. There's an x and y. X is pointing to us, y and then z is pointing to the thing. Okay, so there's some coordinate system here, and now let's say I have a data point XYZ on the things, okay? And now let's say we put the location of the plane that's z minus 1 equals -1, that's basically behind the center of projection. That's the center of the barrier. Then what will happen in this case is that we will project this onto the scene like this. So can anyone tell me what that coordinate is? Or how you will solve this coordinate? Okay, simple geometry, right? You know, z is here. And what you will know is that you'll use a very simple trick that's called similar triangle. All right, so you probably learned this in high school. So similar triangle, because this triangle and this triangle are similar triangle. And then what you will do is that you can work out the math. This is z, and this is minus z. Then what this guy will be minus x divided by z, and y minus y divided by z. Yes. Yeah. So if you look at this, there's a triangle here, and there's a triangle here. Yeah. So because their angles are all the same. So it's a similar triangle, which means that the ratio between the lengths is the same. So you can write this down with a z divided by x, and it will get you this solution. Okay. So you have this x minus x divided by z and y x minus y divided by z. But we don't really like these negative numbers, right? So this negative number is annoying. Every time I need to write this. So a typical things people usually do is that this guy, even though it's physically correct, because the sensor is behind the center of projections, but mathematically, if I can move the sensor in front of the center of projections, then I get rid of that minus sign. Okay, I get this one. Sorry, I get this one. All right. So this is where you'll see a lot of like the camera looks like look like this. But even though it's physically incorrect, but mathematically they are equivalent. Okay, you just put like you cannot put the center of projections in behind the sensor, but because this mathematically it's more convenient, so that we don't need to deal with this always deal with the minus, then it's easier to work with. Okay. All right, so so now we see this very clear mapping between x, y, z, and x this is x, y, z in the 3D world, and to the like x, y, the like horizontal and vertical point in the image plane, right? So essentially we're done, right? So we just need to describe this transformation. The main problem is that we don't really like this transformation. Why is that? Because this is a nonlinear transformation, right? So it's from xyz to x divided by z, y divided by z. So this guy is called a projections, right? Projecting 3D world onto a 2D plane. The main problem is that this is a nonlinear transformation. So this is kind of every time I need to do this nonlinear processing. So this is bad, okay? So the main idea here is the following. So let's say we have this XYZ, and what we could do is that we don't want to work with this nonlinear projections. So the main idea is that if I just add a 1 at the end, then I can write this nonlinear transformation from XYZ to 2D plane, that nonlinear transformation as a linear transformation. Okay, so here's how it works. So again, I don't do anything. I just XYZ. I just add a 1. Increase that into a homogeneous coordinate, and then what will happen? Okay, and then I can write the following. So this homogeneous coordinate, and I write this is a projection matrix, right? This projection matrix that basically x, y, z. I just take x and y and z. Okay, the output of this is just x, y, z. Okay, so and now because this x, y, z, if I want to convert the homogeneous coordinate back to the original coordinate, I just divide it by the last coordinate. Okay, and then I'll just get that in the last coordinate. Okay, so now I have a very convenient way. Instead of saying that, okay, it's from XYZ to this guy is a nonlinear transformation. If I represent this XYZ in the homogeneous coordinate, then this relationship can be written as this projection, right? As a linear relationship in this space. Okay, so this is called projection matrix. It becomes a linear transformation. So we like linear transformation because you can compactly write this down as a matrix vector multiplications. Okay, so far so good. All right, so now we have this linear transformation. But so far we assume the distance between the center of projections to the sensor, we assume that they are 1. And the distance between the center of projection to the sensor, there's a specific name called focal length. They are co-focal lengths. And instead of saying that it's one, you can actually move this to any locations. Okay, so it's you can move this to any location, and specifically the mapping between them is just a scaling matrix, right? You imagine that you have a large focal length, just like if you see any sports photography, you will see the lens is very long, and that has a long focal length, right? So they can see the object that's far away. So then you add this matrix. Okay. All right, so we are trying to progressively building up the camera models. Okay, so now we have this, right? Where we have a projections, and then once you projections, and you can you have this f that correspond to the scaling of the scene. Okay, so you have a focal length, and then what we want to do is that but now I give you this will give me the x and y coordinate in the image plane, but this will give me like the center here, it looks like this, right? The center here is the xy, the center looks like this, right? So on the y, the x direction is positive, and then so this part is positive, and this part is negative, right? This part is positive, negative. But the problem is that that's not how our coordinates in the image was called, right? So in the image coordinate, you may have something like this, right? Or the other way, like you have an x and here and y is there, okay? So you need some kind of transformation from the camera coordinate system to image coordinate system, okay? You need to have these things. So the distance, this transformation is just shifting between this location, right? So what we can do is to just add this scaling matrix, but add a translation part. Okay, we call it U naught V naught. That is just the coordinate of this guy. Does it make sense? So that when I project at any point onto the image space, I know that this point is 0, 0. Okay, this point 0, 0, and the center is U naught V naught. Okay. Does it make sense? Yes. Previous line. This one. Oh, before. So before it was just this. Projection equation, yes. Yep. This XYZ is a 3D point in our space, right? In the world coordinate. And then when you have a camera, look at that 3D point, you want to know the relationship between the 2D point on the camera and the 3D point, right? So the way you describe this is that you project this XYZ onto the camera. And this is a simple expression to say that, okay, previously we showed that this transformation is a nonlinear transformation, right? From xyz to x divided by z to y divided by z. This is nonlinear transformation, but we don't want to deal with nonlinear transformations. So we change this xyz to homogeneous coordinate system. And in the homogeneous coordinate system, we can describe this projection as a simple linear transformation. Okay, so that is the whole rationale of why you want to do that. Does it make sense? And this is just show you that basically this, if you have this matrix multiplied by this vector, you get the x, y, z, and that's still in homogeneous coordinate, and convert this into the Euclidean, the original coordinate R2, you get this. Right? So from this guy to this. Okay. So this is like progressively building up things, right? So we start with this XYZ and then projection, and then we model the focal length because you could have focal length, and also, but right now the 0, 0 is at the center of the pixel, center of the image. But usually we refer the 0, 0 not at the center of the picture. All right, it's usually is somewhere else, and therefore we want to compensate this XY shift, right? So that's why we add U naught V naught. Okay. All right, so we're almost done. Let's see, and this is called projection, right? So we have this projection matrix. And what you usually can do is that you can write this down as on the left-hand side, this matrix is called K matrix. And here you have identity and 0 here. And this K matrix, there's a name for this, right? So this name is called intrinsic matrix because it's intrinsic to the camera itself, right? So for any camera, they have a particular focal length and the size of the U naught V naught. Okay, so this part is a projection matrix. Perspective is called perspective projections from 3D to 2D. And there's a transformation from 2D to 2D. Okay, from 2D image, and it has some scaling caused by the focal length, and there's some origin shift here. Okay, so you have this like K image to pixel and so basically you have a camera to image and then image to pixel. Okay, so there's some more steps involved, right? That is like once you have from 3D to camera, and then you usually will normalize this to 0, +1 to -1, and then you re-normalize this to particular image size. So this is helpful because you can now deal with any resolutions, right? So you can, if you describe this way, it doesn't matter what's the resolution of the image. You kind of remove that out of the equation. So you can deal with maybe this is 256 by 256, but if you have larger size, it only affects this way. So this camera to image mapping is still the same. Okay. So this is done in kind of a typical PyTorch 3D or other 3D pipe libraries. Okay, so what's missing here is the following. So now we describe everything from the viewpoint of the camera, like from the viewpoint of the camera, that's the center projection of the camera. But sometimes we don't do this, right? So because what if I have a multiple cameras? Then which coordinate system should I use? So usually you have something called a wall coordinate. Okay, you have a wall coordinate that describe this XYZ, right? The wall coordinate can be everywhere, like it could be this point, that point, and so on, right? So you can, but once you set up a origin of the world and some orientation of the world, then any point in XYZ is that point is expressed with respect to this wall coordinate. Okay. So right now, what we need to do, and the camera is somewhere in the world, right? So somewhere in the world that has this coordinate system. So what we need to do is to compensate. Previously, we know if XYZ, here when we say XYZ, what we mean is that it's XYZ from the viewpoint of the camera. Okay, so from the viewpoint of this camera coordinate system, these are XYZ. But now our XYZ is not in the camera coordinate system, it's in the wall coordinate system. So which means that we need to kind of first map from the wall coordinate system to the camera coordinate system. Okay, so can anyone tell me if I have a 2 coordinate system, what's the transformation between them? I have one coordinate, another coordinate. How can I align these two coordinates. Yes. So you first need to translate the data translation, right? But what else? You have a transfer basis, yes, correct. But in terms of the actual operation, well, what will you do if you want to align two coordinates? Yes.
Is it a translation rotation?
Exactly. You have a translation and rotation. Okay, so this is the coordinate system for world. And so what you do is that you have a translation that is the translation tx, ty, tz. This is where the world origin is from the eye of the camera coordinate system, right? And then at the same time, you have a rotation. So this is just the translation. And then at the same time, you have a rotation that describes the difference between the difference rotation between the world coordinate system to the camera coordinate system. Okay, so if you look at this, so now you have the XYZ that's in the world coordinate system, then they will first rotate it and then translate it so that now this point is described after this part. By the way, I can simplify this. So I start with a 3D point in the world coordinate system, right? And that world coordinate is somewhere, it can be arbitrarily set, right? So it's more general, like any point in the world coordinate system, I first, I try to describe the same 3D point in the world coordinate system, but from the eye of my camera, okay? So I need to have wall to camera transformation, right? The same point, original XYZ is in the world coordinate system, but if I do a rotation and translation, I can describe this from wall to camera. So now if you look at this, this is still XYZ one vector. That vector now is maybe called X prime, Y prime, Z prime. And that vector is a 3D point in the camera coordinate system. And so now if in the camera coordinate system, we can project them onto the image. So you have a projective matrix like this. And once you project it onto the image, you can scale it and shift it, scaling according to the focal length and shift it according to the size of the image. Okay, you have a camera to image coordinate matrix. Okay, so this is the whole pipeline from a 3D point in the world coordinate system, and we express them in the camera coordinate system, and then project it onto image and scale it and shift it. Okay, sounds a little bit complex, but you can actually simplify this into this, right? So because it's a projection matrix, here you just drop the last one, so you get something like this, right? So there's a name for these metrics. The first matrix is called intrinsic. That's because it's particularly for the camera. And there's another matrix that's called extrinsic. Yes. Una Vina is basically the image size. That basically says that what's the center of the image? What's the coordinate of the center of the image? Because if we found that, like when you do the projections, the center is 0, 0. But when you load the image, the coordinates, you don't represent the center as 0, 0, right? We represent the top left or bottom left as a 0, 0. What was that? Yeah. Yes. Okay. So this is called perspective. This is a linear camera model, right? So it's really convenient because it's a camera model that describes from XYZ to 2D plan, and everything is linear. Okay, linear transformation. So which means that when you have linear to linear transformation, which means that later on, if I know the correspondence, I can basically solve like a similar thing, right? I can solve for these unknown variables. Okay. All right, this is the most general, any camera that you have usually can be described in this way. But there are some other simplified version of the transformation that's called scale orthographic transformation that can be used to describe something that's very far away, right? So in this case, you can think about transformation is just kind of like you have a 3D world and just snap them onto the image. So some example, this is particularly good, useful for say game design. From this viewpoint, you can see that all the parallel rays, parallel lines are still parallel. So here is an example of how you can capture orthographic projections. It's also a way to form an image, right? So it looks like this. If you want to capture a camera, capture a picture, you just do this. And you can see, you can have an image, right? You just snap the 3D world onto the 2D plan. Okay. All right. So it has some application. For example, the reason why you can do object detection is because you assume that all this the further away object further away, they are typically similar, right? So that's why you can do the sliding window detections. Right. There's some other things, for example, radio detection, where some wide angle view, wide field of view cameras, they usually have this kind of transformation that's nonlinear, but you can use some simple parameter to undistort the image. All right, so let's talk a little bit about like lenses. Okay, so typically we use a camera. We only assume that all these are just just a pinhole. Okay, but how do we do this? How do we actually be more like get closer to what we have on our phone? Okay, so let's look at this. So again, this is a tree. Then we want to capture the things. Okay, so here we have a bunch of sensors, and then if we want to capture the things, the problem is that the same point in the things map to different pixels. That's why you get something very blurry, right? This is bad because now every point maps to the same set of sensors. So you get like every sensor receive lights from everywhere. So it's become blurry, right? So let me accelerate this. So the idea is to increase the barrier. All right. So you have this increased barrier. So now this barrier is called pinhole, right? So you have it, and then the size of the opening is called aperture. So now you have every point, every line corresponds to the unique point on the scene. So this is why you get a sharp image. Okay, you get a sharp image here. But you can see here, like what I show here is that this image is very dark. Can anyone tell me why it's dark? Why kind of pinhole camera is dark? Yes. Because it block most of the light, right? So this is a problem, right? So yeah, so on one hand, it's good because it's sharp. On the other hand, it's low PSN, it's a signal to noise ratio. That's very dark, right? You can actually make a pinhole camera yourself, like you just puncture a hole and then you could be able to see this. So maybe a simple way to address this is that let's say let's just increase the aperture, right? So my aperture here is small because I block most of the light. So maybe what I would do is just increase the aperture, right? Because we block most of the light. So like just increase the aperture like this. Okay. So now you see what happened. Okay. So now you indeed for every location on the pixel sensor, you actually see multiple light. You receive more lights. Okay. So you get less dark. you get more signal from the scene. But this you address this high SNR problem. But what is the downside of this? Any idea? Yes. Yeah, now blur, right? So you have this kind of trade-off, right? So you get blur image. Okay. Right. So you get something like this. So how do we resolve this dilemma, right? So people trying to design a camera that can capture high sharp image, but at the same time it need to be kind of high PSNR, right? So previous the model that we have, the simple model we have, like blocking the barrier, doesn't really work, right? Because you have to either increase the barrier or decrease the when you increase the barrier size, you get higher PSN, you get more light, but those lights are not located at the same point. Okay, so this is the dilemma, right? So we want to get a high sharp image and high PSNR, high SNR. So we want to get the both. Okay, the main idea is to introduce a lens. Right? So every camera has a lens, right? The lens help you focus light so that you can you get more light. You can increase your aperture without, but at the same time you can have the lens kind of like any light comes through this lens will be able to focus onto the same point. Okay, so the result of the dilemma, right? So every point you spread out all the directions, but you have a lens that kind of focus them onto the other side. Okay, so yes.
Why couldn't you just like scale the values?
Okay.
Like, why couldn't you just artificially make it more bright by scaling?
You could, but every sensor will have a noise. Like you cannot like basically it's trying to every pixel is trying to count how many photons are hit that particular CMOS sensor.
Just multiply it by X or something.
Yeah, you can multiply by X. The problem is that you have noise, like those sensors. If you don't have a lot of photons that hit those pixels, you will have a lot of noise. So this is where if you play with the DSLR camera or maybe in your phone, they have this ISO number that essentially is trying to like apply that constant, like multiply by 100. But the problem is that you also when you multiply that by that scale, you also amplify the noise. So
you can just get less photons just random.
Yeah. So you have the noise is always there. So the best way is to get longer exposure to get enough photons so you actually know what the actual value is. All right, so how does thing? So usually we assume that it's a lens, and then we assume this so-called a thin lens model. Basically means that the diameter is very thin. It's a lens that is very thin. So how do thin lens model focus light onto the same point? Okay, so basically they have two properties. The first property is that if a light ray pass through the center of the lens, it doesn't change the direction. So it just passed right through. That's the first property. The second property is that a parallel rays, if I have a ray, will converge onto, if I have a parallel ray comes into this lens, it will converge to a point on the other side. Okay. And that point is called focus plane. Okay. So you can see that any parallel ray from any directions will converge onto one plane. That's called focus plane. Okay, this distance is called focus plane. Focus distance. Okay, so this is called focus lens. Focal length. Sorry. All right. So with these two properties, we can now discuss. What if, but this is about parallel rays. but what we care about is a single point, right? A single point as all the can come from maybe this light rate. So what we could do is that this light rate, how do I pass this to, like how to determine where this point will converge to, okay? So what we do is that you have this light rate, you have a point, and this pass through this one, and what we know is that it also, this guy is parallel to this ray, right? And if it is parallel to this ray, then what it means is that these 2 points should converge onto some place on this plan, okay? So how do I do that? So which means that it must converge to, these 2 rays must converge to some place on the plan, okay? It must converge onto this point, which means that I know exactly how this light will bend, okay? It will bend this point, and it will pass through this point. Okay, it's just these 2 properties, right? Any point that any parallel rays will converge onto any parallel rays will converge onto this focus plane, and any points that pass through the center will not change. Okay, so let's try another one. That is, what about this ray? So what we do is that we find the parallel rays that is parallel to these directions, but pass through the center. Okay, you look at this. So now we know where these 2 rays must pass through this guy, okay, onto this, and find the intersection between these 2. So I know this must be here. Okay, now I can draw the line here, and so on. So this is another one. You take this one, you find the parallel rays and pass to the center, and now you get this point. You can draw this, and this is how you know where each point will converge to. Right? So you just follow this process. You can draw any point, any rays coming from the same single point, and how are they converged to on the other side. Okay, let me fast forward. Okay, so you can draw this one. All right, so now it's good, right? So it's with the thin lens model, you actually can, for any point on this one, you actually can converge to here. Okay, this is where the object will be focused. Okay, so people call this sensor. If you put a sensor, which means that if you put a sensor here, and the object is coming from there, you get a high signal to noise ratio, because you can converge all the rays coming out from the same object, and you get a lot of rays, right? More data, so you get a kind of cleaner image. Right? So this is great, but the problem is that like there seems to be no trade-off, right? So what do we miss? What do we lose here? Okay, so here is what we lose. Okay, so let's call this this is called in focus objects, right? So this is the object that's in focus. Okay, so there's some relationship here. So some simple optics. So you have an object height here, and this is going to be the image height, right? So you capture an object, like there's a tree here, in the image, you have an image height. That's the image height here. And what's the relationship between them? Okay, so you can have, again, you have a similar triangle. You have a similar triangle here. So this guy is here, this guy is here. So, and this guy is the focus, then this here, this triangle is the same as, is similar to this triangle. Okay, so what you can do is that you have a magnifications between the image height and object height is really basically related to the sensor distance and object distance. Okay, we'll use this later on. Okay. All right, so So you can also have this other relationship. You can also find these other two triangles, and you can describe this in this way. All right, so let me see. Okay, so there's a simple, like with all this derivation, what we really want to show is that there's a relationship between the object distance and the focal length, and the sensor distance. Okay, this is basically where the things will be sharp, and this is called Gaussian length formula. Okay. All right, so how do we apply this? Okay. Okay, so the main thing it seems that we saw completely like it's win-win solution with this lens, but there's something that we actually trade off with this. Okay, the thing is that it seems that everything is sharp, but it's only sharp for point on this on this object distance, in focus object distance. Okay, if I have maybe there's a dog here. If there's a dog here, it's further away from the focus tree. Okay, so what will happen in this case? Like this one, you can see now because they're not really in focus. So what happened is at that point, the point like reflected light from the dog pass through the lenses will converge all this light like rays, but they will converge before you hit the sensor. And this is why you can now see that all these points become spread, those light rays become spread out onto the sensor. And this is where the defocus blur comes in. Okay, so whenever you capture something with your photo, you'll find that maybe some places is sharp, but some places blur. So this is a trade-off we have to make when we introduce lens in our camera. Okay, so let's see. And then you'll get something like this: a blur dog. Okay. So let's try to understand how do I predict how much defocus blur that I will have. So imagine that you have this point. Okay, so these are relationship. So if we move this, I want to be able to quantify this how much spread it will be. And there's a name. It's called circle of confusion. Basically, those points. These are the light ray that will be spread across this, right? So the radius of this is a circle of confusion. All right, so what does that look like? So the first one is that you have this distance is called actual object distance. Like let's call this S object, actual object distance. And what you do is that you will have, again, we always apply the similar triangle tricks. This triangle is similar to this triangle. Okay, so now the distance of this is the object height. So this is the object height here, and then this length is basically the aperture divided by 2. Like so the aperture is the size of the the light where you can pass through, like half of the aperture. And this distance is the actual distance minus the distance where the object is in focus, right? So this is this difference. And what about this guy is just the actual object distance, okay? So these two, you know that these two triangles are similar. This triangle and this triangle are similar. So which means that you can, the ratio is the same. So basically you can write this down in this way. Like the object height and the aperture and so on. So and then you can write this down, and at the same time you know that this guy object height and the image height is just the half of the circle of confusions this way. So you basically can write this down like this, okay? So you can describe this guy as the following. So this is the C is the magnification times the aperture times this the difference between these things. Okay. So what's the point of this? Right? So what you can do now is that if you move, you can see that if you move this point across the distance, basically you have when you capture a focus, you focus on some object, the if the object is deviate from the focus plane, you will get something that's blurry, right? So how much blurry that is, can be predicted by this. All right, and in contrast to the pinhole camera, like basically if I only have a barrier without a lens, everything will be sharp. There's no such thing as defocus blur in the pinhole camera. Everything will be sharp. But because we introduce a lens, we will have this kind of property. Like some places inevitably will be blurred. Okay. So how do we introduce the to make that less blur? Any idea? If you look at these equations, what can you change to make them less blur? Like that has higher, larger depth of field. Yes. The sensor distance. Let's see. Is this one the object? This object is basically the sensor where you put us where you focus the sensor, focus the object. Yes. Can you say that again? Yeah, if you move the object further away from the focus plane, this is the focus plane, the object that everything on that plane will be focused. If you move away, that's the S object, it will become blurred, right? Because they do not focus on the right location. So now the question is, if you look at this, and this is how much blur this is coming from this equation. So now I'm asking, like, how do you actually reduce the circle of confusion? Yes. Reducing A. Okay. What is A? Aperture, right? So this comes from the previous case, right? Previous case we say that okay, I want to so here this is what we do. Okay, so you can see that if you in this case, this aperture is very large. When the aperture is very large, what happens is that you don't have your depth of field is very shallow. What it means is that the distance between the focus object and if you deviate from the focus distance, it will become blurred very quickly. Okay. So you can see this, right? So you can become very quickly become blurred, right? So the object will only be sharp, relatively sharp within these regions. So this is where, I mean, if you have a phone, you capture a portrait mode, where you have an object is sharp and the background is blurred. Okay, that's exactly that. But what if you want to capture more like a distance where everything is more or less sharp? Okay, what we'll do is the following. As we talk about, if we reduce A, that is and insert a barrier here in front of sensor, like reduce the aperture, then what will happen? You can see the results. Okay, you see that it actually can go very far without the circle confusion become too big. Okay, so when you want to capture something that you want everything is sharp, you want to reduce the aperture in your camera. Okay. Okay, so you can see that now the circle confusions, the depth of field becomes larger when you decrease the aperture. Yes.
The aperture would
Yeah, it will. So, which means that when you reduce the aperture, you inevitably to reach the same level of SNR, you need to expose, either you want to increase the ISO, basically kind of multiply the constant, kind of boost the value, or you have to increase your exposure time. Okay, increase your exposure time so that you get, like, imagine you are taking the sky, like you want to capture the stars. You have to increase the exposure time so that you get more light, so that you get less clean picture. But at the same time, it's also a trade-off, right? So if you decrease your aperture, so you get something sharper. But at the same time, if you capture stars, the stars move, not star moves, like the Earth moves, so that you get kind of the star trail. So it's all these trade-offs that people need to make. Okay. All right, so this is a kind of more practical settings to really understand what an image, how the image was formed. That today we talk about the geometry of a pinhole camera, like how XYZ map to 2D plan. And here is the kind of more appearance, like the appearance of the image that you usually will have some like a defocus blur, and where that defocus blur come from. In computer vision, we usually don't model this. In terms of 3D computer vision, we typically assume that it's a pinhole camera, right? But in reality, it's not, right? In reality, is there's everything that the photo we capture is usually coming from we capture from camera with the lens, right? So it's important to understand that it's also the kind of the details behind it, and so that but with this you can also use this for other application, right? For example, I think earlier when we showed this, we can use this to learn a mapping so that you can create different you can actually change the focus and then to like, this is actually how this kind of iPhone, you have portrait mode, and I think Android also have some method that if you have an image, you can artificially increase the background blur, and all this come from the understanding of these models. Okay, I guess I'll stop here. So next lecture we'll start looking at how we can calibrate a camera and how we can learn 3D from a single image.